So now that you've learned about molar concentration, now we can talk about molar concentration of ions. So to be able to do molar concentration of ions, there is an additional step of requiring a dissociation equation, right? So we talked about writing dissociation equations before the break. This is where we took generally our ionic compound, we placed it in water, and then we broke it apart into ions, making sure that we balanced out those equations. So anytime you see that something is either talking about a concentration of an ion, either because it's asking you to find one or it is giving you one, you're going to need to write a dissociation equation. And that's because from that dissociation equation, we're going to be able to generate a ratio. We generate a ratio by looking at what number did we balance one thing with versus what number did we balance something else with. So if, for example, we balance both of them with a 1, then we know that for every one of the first thing we have, we're also going to have one of the second thing. But if we balance, let's say, 1 with a 1 and 1 with a 2, then we know that content-wise, we're always going to have double the one that was balanced with the 2, okay? So let's look at some examples to show you what exactly this is going to look like. So here we're given the concentration of potassium sulfate as 0.125 moles per liter. And we're asked to determine what is the concentration of the potassium ion. So because we are asked to find an ion, that's our indication that we're going to have to start by writing that dissociation equation. So we're going to take that K2SO4, because it's already a solution, and we know that it's already a solution because we were given a concentration, we're going to make this just an AQ subscript, okay? So this is then, let's see if I can find my arrows on here. Here they are. This is going to dissociate to give us 2 potassium ions, right? Remember we talked about how the little subscripts over here always get placed in front. The only time they don't is if it's part of a polyatomic ion. So the sulfate's a perfect example of that. This 4 gets to stay down here because that's what makes it a sulfate, right? Remember, if we had more than one of the sulfate, there would be brackets around it. There would be some number outside of it. So we're going to have 2K plus that sulfate ion. Okay, so looking at what we've been given the concentration of that potassium sulfate. So underneath where you wrote potassium sulfate in your equation, we're going to write that concentration of 0.125 moles per liter. Okay, and then what we're looking for is that concentration of potassium ions, right? Because that's what the question asked us to find. So how this is going to work. So we're still technically looking for the same things that we were looking for when we looked for molar concentration. The difference, though, is when I think about the units that I want, because I'm trying to look for the concentration of potassium ions, I still want moles per liter. That's not changing. But what is different is what I want moles of, right? I'm specifically looking for moles of K. That's an awful K, but let's pretend that's a fabulous K. I'm looking for moles of K, that's a little better, plus, right? So if I look up here, because sometimes people are like, well, I already have moles per liter. I don't have to do anything. The problem is this moles is associated with potassium sulfate. It's not the K+, so it actually isn't the moles that we are looking for. But that's okay, we can calculate it. So how are we going to calculate this? We need to get a ratio. So what a ratio is going to do is it's going to allow for us to convert between moles of potassium sulfate and moles of potassium. Why it's going to allow for us to do that is when we look at our balanced equation, we can see that for every 1 K2SO4, I should be making 2 Ks. So if I know, for example, that I have 2 K2SO4, I know I have to have double that for my K+, right? I need to have 4 of it. So how my ratio is going to work is I'm going to look at my balanced equation. I'm also going to think about what units I'm trying to get, right? I'm trying to get moles of K+. So that means in my ratio, I'm going to have to put the moles of K+ on the top. How many moles? Well, what number did I balance with? I balanced with a 2. So I'm going to write 2 moles of K+ on the top, okay? What goes on the bottom of my ratio is going to be the one that I have the information for, which is that potassium sulfate, okay? And my potassium sulfate was balanced with a 1. So on the bottom here, we're going to write 1 mole of K2SO4. Okay, so now when we look at our units, we have this part, right? We just placed this by putting it up here. What we need to do, though, is we need to get liters on the bottom, and we need to get rid of moles of K2SO4. So look over here. This has liters on the bottom. That's good. That's what we want. And this has moles on top. And what is the moles on top of? Well, look at that. We wrote it under K2SO4, so it's moles of K2SO4. So we can do times, and then we can use that the way it is. So we do that over our liters. And then again, okay, we look at those units, right? Because we're always doing unit analysis. We can cancel out moles of K2SO4 because it's on the top and the bottom, right? Remember, we've talked about how if we want to cancel out a unit, it has to be in the bottom in one spot, the top in the other. If they're both on the bottom, they don't cancel, they square, right? And if they're both on the top, same deal, they don't cancel, they square. So now when I look at it, here's my moles of K+, here's my liters, okay? So that's how you generate a ratio. For the most part, it's always what you're looking for on top over what you know. And when you look up here, the reason we write our givens and our question marks under those things is so that I know what actually belongs in my ratio, right? I didn't put the sulfate in my ratio, and that's because there's nothing written with it, right? I don't have any info for it, and I'm not looking for anything for it. So that's why it's not in my ratio. Okay, so now when we go to calculate this, we're basically just going to do 2 times 0.125. We're going to get 0.25, and then we're going to put an additional 0 at the end for significant digits, because our one given number was 0.125, and so it had 3 significant digits, and that's going to be moles per liter. And if you want, you can specify that that is moles of K+ per liter, or you can just write it as moles per liter. Either way works, okay? So this is the other type that you are going to see. So similar to the last one, the only difference is that instead of giving you the concentration, it gave you a mass. So we have a solution is made by dissolving 1.35 milligrams. So a milligram, we need to convert that to grams. So to convert a milligrams to gram, we have to divide by 1,000. So we get 0.00135 grams. Or you could do that in scientific notation and write it as 1.35 times 10 to the negative 3 grams. It doesn't really matter, it works out the same. Okay, we have our volume as 250 liters. All right, now I look at this, I don't actually want to write it this way. The reason I don't actually want to write it this way is because we're being asked for a concentration of an ion. This is what happens when you don't read the whole question before you start writing your givens. So always read the whole question first, right? So a solution is made by dissolving 1.35 milligrams of ammonium phosphate in enough water to make 250 ml solution. What is the concentration of that ammonium ion? So we have to start by writing out our dissociation equation. So we have ammonium phosphate. So ammonium phosphate is going to be NH43, PO4. Okay, in this case, I'm going to start it as a solid. I didn't do that with the last one. Why I'm going to do that with this one is because I've been given a mass being placed into a solution. Okay, so we have our arrow. Well, it's not a very straight arrow. That's okay. And over the arrow, we're going to write water to indicate that it has been placed into water, okay? Then we're going to dissociate this. So here's those brackets, the 3 outside of brackets. That means I have 3 of those ammonium ions. Okay, it's now going to be aqueous because we placed it in water. And we have that phosphate ion. Okay, so now that we have our dissociation equation, now we're actually going to start to write out those givens, right? So if you think about it, we're being asked for the concentration of that ammonium ion, right? So this is what we're trying to find. We're trying to find that concentration. So what we've been given is the mass of the ammonium phosphate, right? So we know 0.00135 grams. Because I have a mass, I'm going to need to go get a molar mass. Okay, and molar mass for ammonium phosphate is 149. Oh, that's not right where I want it to. 149.12 grams, and that is per mole. Oh, I'm having issues with my computer here. Okay, and then last thing we were given was that volume. We're going to write that volume over here with our solute, even though really it kind of goes here, but it just tends to make it easier. All right, so now we've listed out all our givens. Again, we want to do the same thing we always want to do. We want to think about what are the units that we are trying to get, right? And we are trying to get moles per liter, but specifically, we're trying to get moles of ammonium ion per liter, right? So we have to make sure that we are thinking as we go through our calculation that ultimately the unit I want to get is going to be moles of that NH4 plus over liters. So we've talked before, but it doesn't really matter if you want to place the liters first or you want to place that moles of ammonia first, as long as you're making sure that everything else is gone and that's what you're left with, right? So some people like to start with the liters first because they're like, well, I clearly have that right here. So you can definitely do that. So do that. To place the liters, we know it needs to go on the bottom. So we're going to do 1. And then we're going to put that over that 0.250 liters, right? So now we've placed the liters that we need to get. The next thing we need to do is going to be to place that moles of ammonium ions. So when I look at my givens, this is grams. This has moles, but this is moles of ammonium phosphate, which isn't what I want. This is liters. So when I look at all these givens, this isn't anywhere in there, but that's okay, because I can get it from my ratio, right? Remember we talked about making a ratio. So when I think about what needs to be on top, I need moles of ammonium on top. So I'm going to go to my balanced equation. There's 3. So we're going to say 3 moles of that NH4 plus. Okay, what we're going to put that over, well, I'm not going to put it over the phosphate because I don't know anything about the phosphate, but I am going to put it over the moles of ammonium phosphate because I have a whole bunch of info for that. So again, this was balanced with a 1. This is going to be over 1 mole of that NH4 3PO4. Okay. All right, so now we're making some progress, right? We have the moles of NH4 plus, we have the liters. Those are the 2 parts that we want. Now we need to start getting rid of stuff. So we need to get rid of this moles of NH4 3PO4. How are we going to get rid of that? Well, we have that over here, right? We have moles of NH4 3PO4 and the molar mass of it. So we're going to take the molar mass. We are going to flip it so that the moles goes on top, right? And we're going to write moles of, let's see if I can just copy paste. Oh, not really. That didn't really work either. Hold on. Okay, problem solved. Made the font a little smaller. So now we've gotten rid of the moles. Next thing we need to do is we need to go ahead and get rid of those grams. So we're going to times by that 0.00135 grams. We can just put that over 1, right? So grams are canceled, moles are canceled.